The objective of this lesson is to solve problems by creating a line plot with a fractional scale. In previous years, students learned how to create and interpret line plots. In this lesson, we will be combining that experience with our knowledge of fractions to analyze a line plot with a fractional scale. We will then use context from a written problem to add data points to an existing line plot. Let's begin by examining the following line plot, which shows measurements of student growth over a year. We can count the number of dots, each representing an individual student, to see that 34 students are represented. In this chart, dots are used instead of X's to show students' growth. Since dots are sometimes used, line plots are also known as dot plots. Notice that this line plot does not begin with 0. Since the range of data is limited between 2 1/8 inches and 3.5 inches, it was not necessary to include 0 in the scale. When building a line plot, noting the smallest and largest values can inform a reasonable range of values for the open number line. Notice also how the scale of this line plot does not include a label for each tick mark. This means we may need to calculate the value of unlabeled tick marks based on our understanding of the scale and fractions. As we continue to look at this line plot, we can see a point of data far removed from the main grouping. One student is shown to have grown 3 1/2 inches, more than any other student in the group. Additionally, the most common amount of growth is unlabeled, but lies between 2.5 and 2 3/4 inches. We can determine the measurement to be 2 5/8 inches because the scale between 2 inches and 3 inches has been marked off into 8 sections, and the data lies on the 5th mark. We know this is the most common measurement because more data points are located along 2 5/8 inches than along any other measurement. If we wanted to compare the student with the most growth and the student with the least growth, we could discover the difference by subtracting the measured values. 3 1/2 inches subtracted by 2 1/8 inches is 1 3/8 inches. The student with the most growth grew 1 3/8 inches more than the student with the least growth. Next, we will add a few additional data points for students not included in the current set. Tim measured 55 1/4 inches, but now measures 56 7/8 inches. How much did Tim grow? Plot his growth on the line plot. Additionally, Sam grew twice as much as Tim. How much did Sam grow? Plot his growth on the line plot. We are unable to calculate Sam's growth without first discovering Tim's growth, since we only know Sam grew twice as much as Tim. For this case, Sam's measurement is dependent on the value of Tim's measurement. To determine how much Tim has grown, we first need to find the difference between his earlier and later measurements. We will subtract 56 7/8 inches by 55 1/4 inches, which is equivalent to 1 5/8 inches. Tim grew 1 5/8 inches. Looking at the line plot, we have to determine which unlabeled mark is equivalent to 1 5/8 inches. 1 5/8 inches lies between 1 4/8 inches and 1 6/8 inches. 4/8 is equivalent to 1/2, while 6/8 is equivalent to 3/4. This means that 1 5/8 inches lies between 1 1/2 inches and 1 3/4 inches, or this position on the line plot. Since we now know Tim grew 1 5/8 inches, we can calculate Sam's growth by multiplying 1 5/8 inches by 2, or by adding 1 5/8 inches to itself. 1 5/8 inches added to 1 5/8 inches is equivalent to 3 2/8 inches. The equivalent fraction would be 3 1/4 inches. Sam grew 3 1/4 inches. We can add Sam's growth to the line plot by looking at our line plot scale and adding a point in the correct position. The objective of this lesson was to solve problems by creating a line plot with a fractional scale. We met this objective by looking closely at an existing line plot to identify unique characteristics. We also calculated new data points and added them to the line plot.